Thank you, and thank you very much for the invitation to speak, and and congratulations on another great meeting, and particularly for holding it virtually this year. Thanks to Professor Chew and the whole team for getting it together, and I'm pleased to join you at the last lecture of the meeting. My brief today was to speak about the future of AI and colonoscopy, and actually I'd like to put the message out there that the future actually is here right now. These are my disclosures with Olympus and Boston Scientific. Colonoscopy is well known to be not perfect. It does not assure protection because of the reality of interval or so-called post-colonoscopy colorectal cancer. Colonoscopy is less effective in the proximal colon, and interval cancers that occurred generally reflect missed rather than new lesions. There is a strong association between the individual endoscopist and the level of cancer protection offered by colonoscopy, and it's this operator dependence that has driven new research into technologies to improve colonoscopy. Interval cancers occur more commonly in patients from endoscopists with low adenoma detection rates, low cecal intubation rates, and who are non-gastroenterologists. Detecting adenomas at colonoscopy requires a combination of two quite distinct skills or processes. Firstly, exposing the mucosa and looking behind folds, looking behind flexures, the so-called mucosal inspection technique. Secondly, having done that, you then need to see the lesion or recognise the lesion, and there are specific skills involved in that. And it's not actually known which of these two skills contributes the most to colorectal cancer protection. Technologies have been evaluated to improve both looking and seeing at colonoscopy, and the effects have been modest at best. But what's exciting is the promise of new technology to help us see better, to help us to recognise polyps when they're exposed behind folds. Artificial intelligence refers to computer programs that perform functions we associate with human intelligence, such as learning and problem solving. And there's a great review earlier this year in gastroenterology for those who are interested. Early reports of AI and colonoscopy actually date back to 2003-2004, when ex vivo studies of still images from large polyp image databases were analysed. But these studies did not involve machine learning, and they required explicit programming for recognition of polyp features. And live video analysis has not been possible until relatively recently. Machine learning, AI techniques are based on machine learning and a subset of that called deep learning algorithms, where there are multi-layer neural networks. And this process allows the software to adapt and learn without supervision to recognise complex patterns when it has been trained on large data sets. And AI and colonoscopy is just taking off. There has been an explosion of technology within the last 2 to 3 years, with multiple studies now coming out showing the potential benefits of AI for colonoscopy, for detection, diagnosis, quality improvement, and for reporting. And the reality is that AI with deep learning looks likely to, and may actually have already exceeded, human performance in visual interpretation. These are the 4 areas where AI is being applied in colonoscopy, and I'm going to spend most of the time on the first of these, but touch briefly on the last 3. Computer-aided polyp detection, or so-called CADe, is very much here and now. This study was the first prospective study of automated polyp detection in only 55 patients, and it showed an equivalence of adenoma detection, and this study was only just last year. This is the very first randomised control trial of computer-aided detection in China, over 1,000 colonoscopies, showing a 9% difference in adenoma detection rate, largely reflecting the detection of diminutive adenomas by the computer. But since then, there have been an explosion of studies, and here are all of the randomised controls trials that have been published, and they've all been published within the last 18 months to 2 years. And actually the literature on AI in medicine is dominated by gastroenterology, and in particular endoscopy. The meta-analyses, of which there have been 3 published just this year, show a 10% absolute increase in ADR and a 50% relative increase in ADR. It does show an increase in detection of hyperplastic polyps, which may be an issue, but interestingly there has not yet been an impact on the detection of advanced adenomas. But the weaknesses of these studies is that they have mostly been single centre, from the centres where the technology has been developed, non-blinded, and with a relatively low baseline ADR, using systems that are not yet, with the exception of one, commercially available. It appears that the impact of other detection technologies is relatively modest in comparison with AI, with the other technologies being around 1.2, with AI for detection sitting at around 1.5. So it certainly holds much promise. And if a 10% increase in ADR was to occur with AI, this would translate to a 50% reduction in interval cancer rates extrapolated from the 2014 Californian data from Doug Corley. Now, excitingly, computer-aided detection is here and it's commercially available. These are the commercially available systems that have now achieved regulatory approval in Europe or in Japan or in Australia. And my role today is to talk a bit about the initial application of computer-aided detection in clinical practice. There are a number of ways that this could work. You can either use one monitor or two monitors, with the software appearing on one monitor and then the real-time image on the other. And then there are various alarms or alerts or flags that can be used to alert the endoscopist to the detection of a lesion. These alerts can either be visual or they can be audio, and visual alerts can either be direct by flashing on the screen where the polyp is, or indirect by flashing adjacent to the screen or putting a mark on a picture-in-picture appearance. In Australia, the ENDO-AID system from Olympus Corporation has just become available, and I've had the opportunity to just evaluate this just recently. Actually, I've had it for about 10 days, and I can provide some initial or interim reflections on its application in real-time colonoscopy. The Olympus ENDO-AID system comprises an open platform termed the Olympus Intelligent Platform 1, and interestingly, this is potentially expandable with the incorporation of future CADe modules such as diagnosis and other forms of CADe. And in fact, it's proposed that it will allow the installation of third-party CADe programs or algorithms with in collaboration with Olympus. This platform is primarily compatible with EVIS X1. It's not backwards compatible with the 190 or 290 series. However, if you have the EVIS X1, the new processor, you can use 180, 190 or 290 series scopes in addition to the newer generation scopes. And this system provides for a real-time display without the need for a second monitor. ENDO-AID integrates nicely with EVIS X1, allowing a single monitor and control from the scope. So as you can see from this screen, the scope allows you to communicate with the processor and then onto the OIP and then to the monitor. You can switch the CAD with your scope. You can switch between modes with the scope, and it also promises to integrate with compatible reporting systems, which is very, very interesting and exciting. ENDO-AID works with white light and with the new imaging modality called TXI, Texture and Colour Enhancement Imaging, but not with NBI. NBI is reserved for diagnosis at a later date. There are two detection modes. There is the normal mode where you have a flag applied in the corner of the visual field and a picture-in-picture showing you the actual lesion. And then there is the target mode where the green square flashes on the screen where the actual lesion is. And you can also have two sensitivity modes, type A, which is high sensitivity but lower specificity, and type B, which is higher specificity. The aim being that you can toggle between these modes, potentially to try and reduce the impact of false positives. My initial impression of this system is that it allows seamless integration with routine practice. It's effortless, it's just push-button technology on the scopes, and there's almost no setup required each day or each case. It's just simply there on the stack and it can be switched on. Here are some initial videos of my experiences with it. Here is a diminutive adenoma in the proximal colon that's been located here, as shown by the green flashing screen, which persists. And as you get up close with optical enhancement, I'm sure you would agree that this is a typical type 2 nice classification diminutive adenoma. Here is a further lesion, a larger adenoma, flashing madly with the detection technology, which again on closer examination is a single lesion typical for an adenoma. Here is a proximal colon serrated lesion, again picked up with the detection technology, the green flag, highlighting it, and again on NBI, the typical appearances of a nice one sessile serrated lesion. Now, what about the other mode. So this is so previously those 3 videos were the target mode, and now here we have the normal mode, where on this small image on the left you'll start to see a polyp appear with a green square around it. So here the flags are showing on the corners of the endoscopic image, the real-time image, with a small image to the left allowing you, and this just allows you to choose which of the 2 forms of flagging you prefer. My personal preference after a short period of use is that I don't actually tend to see the image on the left-hand side with this mode, so I'm tending to prefer the target mode so that I can actually see the green flags in front of me. But you need to think about false positives, and there are various methods and suggestions from others to reduce distraction from false positives. For example, on insertion, I don't use CADe, I simply turn the CADe on when I get to the cecum. Once you reach the cecum and you turn the detection on, you attempt to reduce false positives by maximising insufflation, by cleaning up as usual, so clean the lumen, apply some ethicone wash to remove bubbles. I tend to, you can adjust the sensitivity. I've been tending to use type A just to understand how sensitive it is, but I do prefer target mode because I simply just don't recognise lesions that are in the periphery, flags or alerts that are in the periphery of the visual field. And then during polypectomy, I tend to switch to the normal mode so that I don't have the green square in front of me. So here you can see the typical false positive. So here the false positive, I've just paused it, flashes up momentarily and then disappears. So once it recognises that it's not a lesion, the green square will disappear. So here is another one coming up shortly. So this is another false positive from a previous suction polyp. And as I continue to search and apply good mucosal exposure techniques to allow the software to recognise lesions within the visual field that has been exposed. Again, you'll see another false positive shortly. But it's the transient green screen that is the giveaway for it not being a true positive. I'll keep moving there. Now here is the impact of polypectomy. So here is a further adenoma, this time in the sigmoid colon. I'm ready with the snare, and when you perform polypectomy with the target mode on, it may be distracting. So I've just left it on to show you, but you can toggle it off very easily. So here's a simple cold snare polypectomy of a small adenoma effective, but you can certainly see the green squares potentially being distracting, but that can be easily adjusted. I've had little experience or limited recognition of false negatives, but I do have one case to show you. So here is a patient with serrated polyposis. This was a long procedure with multiple small and diminutive and some large serrated lesions. And I wonder if you can see the large serrated lesion that the software is not detecting. So it will actually detect a number of smaller lesions. You can see them showing up here in the green screen, but in the center of the screen here, you can see a large sessile serrated lesion that is not flashing. Here, if you can see my mouse, that's a lot, and it doesn't flash until you get closer to the lesion and it recognizes it there. So it's interesting that for some reason this software hasn't picked up a large serrated lesion. I must confess, in this particular case I had washed it, but I have seen some other serrated lesions where I hadn't washed off the mucus cap and it was still not detected once it reached a certain size. That's my only real experience with a false negative. Just to finish off, I'll make some comments about other applications of computer-aided diagnosis and so forth. So computer-aided polyp diagnosis is the next exciting development, and there are several projects underway here. For example, ENDO-Brain in collaboration with Cybernet and Olympus is a system out of Japan. CADe from Fujifilm is available and it allows real-time diagnosis, but there are others that are under development. There are not yet any prospective clinical trials of computer-aided diagnosis. Just to note that CADe diagnosis does require image enhancement, and it will require either electronic enhancement or chromoendoscopy enhancement. And obviously there are then moves to try and merge the detection and diagnosis technology into a single maneuver so that you get both a detection and an answer, a diagnosis at the same time. There is some very exciting developments in quality measurement, and AI can actually begin to start measure quality in real time. AI can do far more than just find and diagnose polyps. It can firstly improve the quality of colonoscopy, and then it can start to measure the performance of colonoscopy in the unit. So in AI quality improvement, it's about measuring the quality of mucosal exposure. It can measure the withdrawal speed and the extent of insertion. There are systems under development that evaluate the percentage of mucosa visualised. So it gives you a fingerprint, if you like, of how well you have exposed mucosa, and also measures your speed of withdrawal. And there's one study just recently published this year that measures whether there's been slippage back within the colon and you've just lost view of a large section of colon. Future technology is all around reporting and analytics, and this is very interesting. There's the significant potential for AI to actually complete a lot of our documentation. AI can recognise endoscopic landmarks, so it will be able to document whether the procedure was performed to the cecum and to the ileum. It will allow detection and documentation of preparation quality and recognition of specific endoscopic tools such as biopsies or snares, particular snare choices, and importantly it will measure insertion times, withdrawal times and washing times. And this is from the recent ASG technology review, where in the current practice on the left you can see what happens where there's lots of separate processes that are not integrated, but AI may allow all of this to be performed at the point of care so that you can see the patient, perform the procedure, measure the quality, make the diagnosis of the appropriate lesions and assign a surveillance interval, report your quality and report all of that back to the referring physician. So that's very exciting. A word of caution just to finish. Of course, there are always caveats about new technology, and this is occurring with such rapidity, and adoption is likely to occur similarly fast. There have been relatively few studies. It's not like there is a wealth of evidence across multi-centres. Most of the studies have been performed in single centres, so there is a need for longitudinal prospective studies in a multi-centre basis. There is the risk that AI will allow the de-skilling of endoscopists who begin to over-rely on AI and who'd never developed the techniques of polyp recognition. There's the potential for overload, information overload from false positives and from apparent misdiagnoses. And finally, there is the ever-present concern, particularly in Western practice, of medical legal implications and responsibilities. Who made the diagnosis? Is it the endoscopist or the computer that's done that? And that's not yet been resolved. And in most centres, most context, there is not yet any promise of reimbursement for this technology. AI does not replace the endoscopist. Mucosal visualisation, as I've said, is still required. It does require good bowel preparation, good mucosal cleansing, and meticulous and systematic exposure of hidden parts of the colonic wall, requiring insufflation and exposure. So AI ADR only reflects what is seen within the visual field and not areas that are not exposed. There's also the potential for endoscopists to gain the ADR standard because only one adenoma is required to achieve a detection positive. Rapid AI enhanced endoscopy may be facilitated by AI, and in fact AI may not translate into protection against colorectal cancer if this is the case, and there may be an argument for different quality standards for AI, and in fact good quality endoscopists may be able to perform quicker withdrawals, but even find more adenomas. So this is a rapidly moving field. We need clinical validation in high quality prospective randomised trials. AI should improve the quality of colonoscopy, and it certainly promises to improve the efficiency and the cost of colonoscopy, but we do require assistance to measure and report quality of mucosal exposure, and CADe can't replace physician judgment. So to finish, I summarise by saying AI is here, it's available. CADe systems show low latency, high sensitivity and specificity for polyp detection, and the RCTs are showing a substantial benefit for adenoma detection, and rapid clinical adoption of AI technology is highly likely, and further rapid development and progress should be expected. Thanks very much for the invitation and to speak this evening.